Hello dear students. In today's class, let us try to understand more about the damped harmonic oscillator, its equation and its equation. We will try to analyze the equation of the damped harmonic oscillator to understand various situations under which it can work. So first of all, we derived the differential equation corresponding to a damped harmonic oscillator as d square x by dt square plus 2k into dx by dt plus omega 0 square x is equal to 0. So this is the general differential equation corresponding to the motion of a damped harmonic oscillator. We got this equation by comparing or adding up the forces acting on the system, which is the restoring force and the damping force. So just a modification on these two equations will give you the differential equation corresponding to the motion of a damped harmonic oscillator. Now our next challenge was to solve this differential equation to find x as a function of t. So x as a function of t implies the position of the system corresponding to different time, and that can tell you a lot about the system. You will be able to understand its physical properties such as velocity, acceleration, its time period and so on just from this equation. So that is why it is so important to find out the solution or the equation of motion of the system. Now we had obtained the equation of the damped harmonic oscillator by solving this differential equation as x is equal to e raised to minus kt into a1 e raised to root of k square minus omega 0 square into t plus a2 into e raised to root of k square minus omega 0 square. Here is a negative sign, e raised to minus root of k square minus omega 0 square into t. So this is the equation for x. And when we look into this equation, this can have different forms or different behaviors under different conditions. So let us try to analyze that. Before moving on to that, let me tell you something regarding the behavior of certain functions. So these functions that I am going to mention are something you will see a lot in various physical situations. You will come across these functions in many equations, and let us try to understand the behavior of these functions. So I hope you already know about the function exponential function. So that is something that increases sharply when we increase x term. So if this is x and this is f of x, which is e raised to x, the exponential function will sharply shoot up as we increase x. Whereas the function e raised to minus x is a sharply decreasing function. So if you plot the same function here, e raised to minus x will fall down like this. It's a decaying function. In many cases, you will see terms like e raised to minus kt and so on in various equations. This actually implies something is decaying fast with respect to time. In the case of oscillation, that means a decreasing amplitude or the energy of the system. So it will sharply fall down from an initial value with respect to increasing time. Now, I hope you understood the behavior of e raised to minus kt. There has to be a negative sign here. Positive sign implies an exponentially increasing function, and a negative sign means an exponentially decaying function. So you can see that in our equation, we have an e raised to minus kt, which causes the system to slow down or which causes the amplitude to decrease as time increases. And now the second function that you need to remember is the e raised to ix function. So you can expand this as cos x plus I sin x. E raised to ix actually correspond to an oscillating solution. So if cos x and sin x is coming in the solution, then you can easily understand that there will be some oscillating behavior in the system. For example, in the case of an oscillator, the solution is x equal to a sin omega t plus phi, right? So this actually means that the system is oscillating. There is some sort of oscillating behavior in the system. In the case of oscillator, it is the position which is oscillating, which is varying like a sine function. But in different physical situations, whenever the sine function or cos function or e raised to ix function comes in the equation, that actually implies that the system has some sort of oscillating behavior. Now you have to specifically remember that we need to have an I term here. I correspond to the iota or the root of -1. So then only you will be able to expand it as cos x plus I sin x, and you can get an oscillating behavior. If this is simply e raised to x, this is not the case. The system will not be oscillating. E raised to x is simply an exponentially increasing function. E raised to ix is something different. That is an oscillating function, a function that has an oscillatory behavior. So with this in mind, let us try to analyze the equation that we have in our hand, which is x equal to e raised to minus kt into a1 e raised to root of k square minus omega 0 square into t plus a2 into e raised to minus root of k square minus omega 0 square into t. Now, as I have already said, the initial term is e raised to minus kt, and let us try to understand the behavior of the terms inside this square brackets. We have e raised to root of k square minus omega 0 square into t here, and the behavior of this function will actually determine the behavior of the whole system. So what is this term here? Root of k square minus omega 0 square. This term, it can have different value depending on the relation between k and omega. K can be either greater than omega 0, or k can be approximately equal to omega 0, and k can be lesser than omega 0, and this will determine the different behaviors of the system. First, let us try to understand the case when k is very much greater than omega 0, and that condition is called the case of overdamping. We will try to understand why it is called overdamping after we see the solutions. So as of now, let us state the condition for overdamping is given by k greater than omega 0. And when we look into this equation, if k is greater than omega 0, we can see that k square minus omega 0 square will be a positive quantity, because k is greater than omega 0. That implies k square is greater than omega 0 square, and that implies k square minus omega 0 square is greater than 0. We have taken this omega 0 square to the left hand side. So if k is greater than omega 0, that implies this factor of root of k square minus omega 0 square is also greater than 0. That means it is a positive quantity. So here in the exponential factor, we have a positive quantity if k is greater than omega 0. So let me write, if k is greater than omega 0, then root of k square minus omega 0 square is also greater than 0, is a positive quantity, and I call this term, this positive quantity, as beta. This can be either positive or negative, in fact, because taking square root will yield you both positive and negative terms. So this will be just a simply a real number. It can be positive or negative. There are two solutions corresponding to the square root. One is positive and the other one is negative. And both those solutions will be a real number if k square is greater than omega 0 square. We know square root of a positive number is a real number. It can be either plus or minus. Now, if this number is a real number, then our equation will become, then our equation for x, which is the equation under consideration, this can be rewritten as x equal to a e raised to minus kt into, simply e raised to minus kt multiplied by a1 e raised to beta t plus a2 e raised to minus beta t, or which is equal to a1 e raised to, multiplying these two, I will get e raised to minus of k minus beta into t plus a2 e raised to minus of k plus beta into t. So if you multiply these two, it will be e raised to minus kt plus beta t. Taking a negative sign as common factor, you will get the term like this. Try to do it by yourself. You can find that the first product is a1 into e raised to minus k minus beta into t. Now this is the equation for x. Here k and beta are all real numbers. And when we look into that, this equation has a specific format, right? We have already told the speciality of this function. E raised to minus a constant into t. This is an exponentially decaying function. So here both the terms are exponentially decaying. That means x will decay exponentially with respect to time. So if we try to plot that, suppose this is our x value, which determines the position of the system, and this is the time. We are going to look into the position of this oscillator at different time. If it is a simple harmonic oscillator, we already know it should go like a sine wave or a cos wave, repeating its position at frequent interval of time, at a constant interval of time. We call that as time period and so on. But if the system is overdamped, then its position will exponentially decay. There is no oscillatory behavior for the system. Do you see any sine function or cos function or e raised to ix or it function here? No, right. This is simply an exponentially decaying function with respect to time. Simply e raised to minus a real number into t. So that means the system will slowly come down to its mean position as time increases. There is an exponential decrease in its x value with respect to time. That is why it is also called a damped, overdamped oscillator. The damping is so high that the system is not able to move or make another oscillation. So this kind of motion is also called deadbeat or a periodic motion. There is no periodicity. It is not even making a second motion along the same line. It is just slowly coming down to rest. If you want to imagine such a situation, you can think that we are oscillating our spring mass system in a heavy oil tank. Suppose this system is filled with heavy oil, not water, something with high viscosity, and you move this mass down and make the system oscillate. The system will not be able to even move. What it would do is it would slowly come to rest at its mean position, slowly moving through this thick viscous liquid. So if you are moving the oscillating system to such high viscous liquid, it won't be able to make oscillation. It will simply come to rest from the extreme position. So that is the case of overdamping. That is the case when the damping factor is very high. That means if the system is moving through highly viscous fluid or some atmosphere or some environment where it is not even making any oscillation. It is not possible for it to oscillate in that system. So that is why We call it as deadbeat or aperiodic motion. It is exponentially decaying function. X is an exponentially decaying function. It will slowly come to rest at its mean position. So this happened when k is greater than omega 0. So what was k? K is the damping constant, right? That means if the damping factor is greater than the natural frequency, then the system will slowly come to rest. It will not be able to make oscillations. So that is the case when we consider overdamping. The system is overly damped. And the solutions, as you can see, display no behavior of oscillations. Now coming to the second case, which is often called the case of critical damping. And this happens when k is approximately equal to omega 0. So let us first try to find the solution corresponding to k equal to omega 0. Just for a fun, let us do that. What will happen if k is equal to omega 0? If k is equal to omega 0, then k square is equal to omega 0 square. And root of k square minus omega 0 square will be simply 0. So what will be the solution of x? What will be x values? It will be simply x is equal to e raised to minus kt into a1 e raised to 0, which is 1, plus a2 e raised to 0, which is again 1. So let me call this term a1 plus a2 as c. This is simply c e raised to minus kt. Now this does not provide a solution of the differential equation of second order. Here there is only one constant and we cannot consider this as a solution. So what we will do is to substitute k approximately equal to omega 0 into our equation and try to find out the answer. If k is exactly equal to omega 0, this is the solution, and this does not represent the exact solution corresponding to a second order differential equation. Now if k approximately equal to omega 0 implies they are not exactly equal, but they are very close to each other. That means if you find k minus omega 0, it is not 0, but it is a very small quantity which we call as h square. H is something like 0.01 or 0.001, so that we can say they are close to each other. K and omega 0 are close to each other. Now if you find root of k minus omega 0, k square minus omega 0 square is h square, and root of k square minus omega 0 square can be chosen as h. So choose the substitution like this. K is approximately equal to omega 0 and k square is approximately equal to omega 0 square, and that small difference is called as h square. Now what will be the solution of x? If you make this assumption, x will be equal to e raised to minus kt into a1 e raised to ht plus a2 e raised to minus ht. So this is the solution x, where we have substituted h as root of k square minus omega 0 square. Now to understand this equation more, let us make another substitution. So I hope that you know about the series expansion of the exponential function. E raised to x can be expanded as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So this is the series expansion corresponding to e raised to x. And if x is very small, you can approximate this by the first two terms, because the rest of the terms will be very small. If you square a small number, the answer will be even smaller. The cube of a small number is even smaller. So you can neglect the rest of the terms for small values of x. So here, instead of e raised to ht, since h is very small, we can make an approximation like 1 plus ht plus the rest of the terms. And here, instead of e raised to minus ht, you can make an approximation of 1 plus minus ht plus the rest of the terms. Here, minus ht is the factor in the e raised to exponential function. So, substituting these two values, that means for e raised to ht, you substitute 1 plus ht plus the rest of the terms which we will neglect, and e raised to minus ht as 1 minus ht plus the rest of the terms. We will obtain the equation for x as x is equal to e raised to minus kt into a1 into 1 plus ht plus a2 into 1 minus ht. So, this is equal to e raised to minus kt into a1 plus a2. So, multiply the terms inside the brackets, a1 into 1 plus a1 into ht, here a2 into 1 minus a2 into ht, and take the terms that are common. So, a1 plus a2 plus ht into a1 minus a2. So, this is the value of x, and let me call this term a1 plus a2, which is a constant, as p, and a1 minus a2, which is another constant, as q. So, we can rewrite x is equal to e raised to minus kt into p plus q into t. So, here a1 minus a2 into h is chosen as q. P is equal to a1 plus a2 and q is equal to a1 minus a2 multiplied by h. So, under these two substitutions, x can be rewritten as x is equal to e raised to minus kt into p plus qt. Now, let us try to find the values of p and q in terms of known quantities. All we know is p is a1 plus a2 and q is a1 minus a2 into h. So, let us try to understand about these terms in terms of the initial position or the initial velocities of the system. To find that, let us substitute the case of an extremal condition, which is t is equal to 0, which is the initial time or the starting time of the system. We consider that at the initial time, the system is in its extremum position given by x equal to x0. Then, this actually implies substituting t equal to 0 into this equation of x. We will obtain x equal to e raised to minus 0 multiplied by p plus q into 0, which is simply p. And since at t equal to 0, x equal to x0, I can write this x as x0. So, from this expression, it is clear that the value of p is simply x0, which is the initial position of the system. Now, to find the value of q, we will have to take the differential of this expression. So, then we can cancel out this t term and try to find out the value of q term. So, taking the differential of the expression given by equation 1, dx by dt is equal to e raised to minus kt into p plus into d by dt of p plus qt plus p plus qt multiplied by d by dt of e raised to minus kt. So, we have used the product rule here in order to find out this differential. first into derivative of second plus second into derivative of first. Now substituting for each of this, we will get e raised to minus kt into derivative of this factor is simply q plus p plus qt into derivative of this term is minus k into e raised to minus kt. Now let us try to find out what will happen at t equal to 0. So at t equal to 0, we choose that the initial velocity is v0. The initial position is x0 and the initial velocity is v0. So substituting throughout the system, the condition for t equal to 0. So this is dx by dt is simply velocity. So at t equal to 0, velocity is v0, which is equal to this term with t equal to 0. The first term is e raised to minus 0 multiplied by q. Then again here substitute t equal to 0, which is p into minus k into e raised to minus 0. E raised to 0 is simply 1. So this is q minus pk, and we know p is x0, right? So this is q minus x0 into k, or this implies q is equal to v0 plus x0 into t. So p is simply x0 and q is equal to v0 plus x0 into t. These are the values of two constants that we had in our equation. So x is equal to e raised to minus kt into p plus qt was the considered equation, and we found out the expression for p and q in terms of x0 and v0. Now substituting for each of those terms, we can rewrite x is equal to e raised to minus kt into p plus q into t. So this is the expression for the position x in the case of a critically damped oscillating system. So as you can see here, we have two separate functions. The first function is e raised to minus kt, which is an exponentially decreasing function, and the second function is x0 plus, sorry, I made a small mistake here. Q is not v0 plus x0 into t, q is v0 plus x0 into k, right? From here, v0 equal to q minus x0 into k. That implies q is equal to v0 plus x0 into k, and that actually implies here again we have x0 into k. So x0 plus v0 plus x0 into t, sorry, x0 plus v0 plus x0 k multiplied by t. This is the second function, and as you can see, that is a linearly increasing function with respect to time. This function is an expression of the form a plus a constant b into t. So this is an expression for the straight line. This is a linearly increasing function. So here two functions are involved. One is an exponentially decreasing function and another is a linearly increasing function. And when these two expressions, when these two functions compete with each other, usually the exponentially decaying function will win. For very small values of t, there will be a small increase for the value of x. But after that, the system will exponentially decay in its position. X value will exponentially decay and the system will come to rest. So if we try to plot the graph corresponding to this condition, what we will obtain is again an exponentially decaying function which correspond to the case of a critically damped system. So as we have seen, this term is only effective for very small values of t. So we can say for very small time, the system will show a slight increase in the displacement, but as time passes, the system will exponentially decay in its position and will come to rest. and no oscillating behavior is displayed by the system under critical damping, K approximately equal to omega 0. And this type of behavior is often displayed in galvanometer, which actually shows a slight deflection and comes back to rest at the equilibrium position when we apply voltage to the system. And now let us try to understand the third criteria, which is the case when K is less than omega 0, which is the condition called underdamping. So if K is lesser than omega 0, then K square will be lesser than omega 0 square, and K square minus omega 0 square will be lesser than 0. That means this term is a negative quantity. And how do you take the square root of a negative quantity, root of K square minus omega 0 square? If this is a negative quantity, its square root will be imaginary. For example, square root of minus 5 is imaginary. In that case, you do it like square root of minus 1 into square root of 5, and you call this square root of minus 1 as iota or I into root 5. So this is how you take the square root of negative numbers. So here this is a negative quantity and you cannot find the square root directly. So what you will do is take the square root of minus 1 into root of omega 0 square minus K square. So this is equal to I into root of omega 0 square minus K square. Because this quantity is now a positive quantity, omega 0 square minus K square is positive, multiplied by I. And I call this term as I omega, where omega is defined as root of omega 0 square minus K square. Omega 0 is the natural frequency and K is the damping constant, and omega will be the new frequency of the system with which the system oscillates. Now let us rewrite the equation for X as e raised to minus kt into A1 e raised to I into omega t plus A2 into e raised to minus I into omega t. Because our equation for X is X equal to e raised to minus kt into A1 e raised to root of K square minus omega 0 square into t plus A2 into e raised to minus root of K square minus omega 0 square into t. Here this term is simply I omega and this term is simply again I omega. Here we have a negative sign, and that is why we had written X as X is equal to e raised to minus kt into A1 e raised to I omega t plus A2 e raised to minus I omega t. So as we have already stated, here we have e raised to ix function, the oscillating function, which actually implies that the system will be oscillating, system will repeat its position with time. But here is another exponential factor that is there in the amplitude of the system, and that means that the amplitude will exponentially decrease. So this is the case of an underdamped system. So let us rewrite this expression. And since the position x value has to be a real number, since it's a physical value, it cannot have an imaginary number, it cannot have an imaginary value, it should have a real value. So A1 and A2 has to be complex numbers. Here we have a complex number here, and in order to counterbalance that, A1 and A2 should be complex numbers. So let me write that since x is real, A1 and A2 should be complex. Now let us simply rewrite the expression for x as x is equal to e raised to minus kt into A1. Instead of e raised to I omega t, we can write cos omega t plus I sin omega t plus A2 into e cos omega t minus I sin omega t, because we know e raised to I omega t is cos omega t plus I sin omega t, and e raised to minus I omega t is cos omega t minus I sin omega t. Now modifying this equation, we will get x is equal to e raised to minus kt into taking cos omega t as common, we will get a1 plus a2 into cos omega t, and taking I sin omega t as constant, we will get plus I sin omega t into a1 minus a2. Now here, this a1 plus a2 and I into a1 minus a2 has to be real numbers for this x to be real, because this is real number and here we have real number. Therefore, a1 plus a2 and I into a1 minus a2 has to be real numbers. But a1 and a2 are complex numbers. Now choosing a1 plus a2 to be equal to a0 sin phi and I into a1 minus a2 as a0 cos phi, we will be able to modify this equation as x is equal to e raised to minus kt into a0 sin phi cos omega t plus a0 cos phi into sin omega t. Now we have seen these kinds of equation. You can take a0 as common. You can rewrite x is equal to a0 into e raised to minus kt into sin phi cos omega t plus cos phi sin omega t. Now you have seen this expression somewhere. This is sin a cos b plus cos a sin b, which is simply sin a plus b, where a is phi and b is omega t. So we can rewrite x as x is equal to a0 e raised to minus kt into sin omega t plus phi. So this is the expression for an underdamped oscillator. Here we have the sine function that actually means that the system will oscillate. But again we have here e raised to minus kt function, which is an exponentially decaying function. In the amplitude of this term, we have that function that actually implies that its amplitude will exponentially decrease. So let us try to analyze this equation by seeing the plot of the function. So we have an oscillating function itself, but whose amplitude will exponentially decay in the case of an underdamped oscillator. We have sine function whose amplitude is exponentially decreasing. So in this picture, this green curve represents the case of an underdamped oscillator. So it's oscillating, but the amplitude seems to decrease in an exponential manner like this. Amplitude is the topmost part of the sine curve, right? Or the maximum displacement from the mean position. So amplitude is decreasing exponentially, but the system as a whole is executing an oscillating motion. So this is the case of an underdamped oscillator. We will detail about the characteristic features of an underdamped oscillator in the next class. First, for now, we have evaluated the three different cases of a damped harmonic oscillator, the underdamped, overdamped, and the critically damped cases. We tried to find out the equation corresponding to these three cases and try to analyze these equations. In the next class, we will analyze the special case of an underdamped oscillator, try to find out its properties, and we will also try to detail about the position time graph of various other systems under critical damped condition and overdamped condition. So I hope this portion is clear for you. Thank you.